On this 15 minutes, we'll launch you right now, and you are up.
Okay, and this is the mouse.
Okay, everyone, here we go. The moon. It is
on. Yeah. Okay, so our DRM group was focused on lunar exploration, and so we made two assumptions kind of right off the bat. One is that we're kind of focusing on the near term, because if we're looking out at 2050, it was getting kind of sad if we hadn't accomplished all our goals by then, because the moon is so close and such a great target. Also, we assumed that we also had accurate landing, so that we were able to land within a small region. And for most of our projects that we were kind of looking at, we were looking at mobile platforms. So as long as we were landing in a safe location, that was great. And then we could just rove to where we wanted to take our science measurements. So the two DRMs that we looked at was kind of a wide area sampling mission. So this was this could use multiple rovers and teams of rovers to go and investigate an area. The example that we used here was for like Marius Hills region of the moon. We also looked at a polar explorer, so a place where there would be limited direct-to-Earth communication, and if, depending on what the comm relay satellite situation is, we might not have as much downlink as we would like for a particular mission. And so I'm just going to flip all the way to the backside. So we ended up doing a lot of work and a lot of brainstorming on different type of mission concepts, and which is kind of captured on this slide. And then we also kind of broke it down into fundamental areas for where autonomy could be injected to make the mission better or possible. And I'm just going to go to this slide because it kind of summarizes everything that we're going to talk about. So we kind of looked at how autonomy can transform lunar exploration. One way would be autonomous local navigation. This includes hazard avoidance and getting around on the surface. One other aspect is using multiple robots or assets together to do a coordinated effort at a particular location. And then we also looked at how you would handle multiple robots and humans and how those two teams would interact, because the moon is a unique place where we can send humans. So there might be humans on the surface or at the gateway or even on ISS or even back on Earth. How are those humans interacting with the robots that we have on the surface? And then another one is adaptive autonomy, which is looking at how the system would learn over time. So as far as for local navigation, we basically kind of said that this would be applicable to both type of missions, whether it was a long duration, high speed rover that was going to cover a large area or a polar prospector. And the reason for autonomous navigation would just be to make the traverses safer, because the rover can collect a lot of data about what's around it and can use that data to help inform and make decisions on where it's going to go and everything like that. And so we used the taxonomy and we kind of broke out into the different areas. As far as what type of technologies this could use, it could use LiDAR or stereo cameras or IMUs or things like that. There were a couple areas of current research that's been going on. Of course, with all the self-driving cars, some of that technology could be used and leveraged. So that's a bonus, as well as some off-road vehicles and things like that. And then, let's see. Yeah, so basically, our ideas were that you could develop a technology to put on a rover that could also help it stay in a sun-synchronous motion around the moon, to where you could extend the life of a mission and not rely on RTG or some other type of radioactive generator. Instead, you could kind of rely on solar power and batteries for most of the mission. And this could also be used in teamwork with other robots, so that you could use one that would mainly be a charging station, and then the others could go off and explore different areas. So I'm going to hand this off to Terry to kind of go over this slide, and then we'll kind of come back and forth. So there you go.
All right, so as Emerson said, one of the things that we were looking at from a DRM point of view is wide area exploration, and for us this could involve wide area sampling. So if you wanted to do, say, exhaustive sample collection in South Pelican Basin, assuming that you had a different strategy than, say, Moonrise, or if you want to do comprehensive local site assessment, let's say that you really want to do very systematic, detailed volatile mapping, Any of those things could be done by single systems, but might work off better having multiple systems working in parallel. And so for us, the assumption here is that if we want to have, say, multiple robots working in parallel, it may be the case that they're too costly to operate multiple systems from Earth, or that maybe it's more effective, more efficient for these to work somehow in conjunction with one another. Or maybe these robots have to operate when we can't have humans in the loop because they're operating perhaps over long periods of time, or maybe even wide areas where it just is not practical to have continuous mission control with that. And so in order to do this, the question is, how do you then create systems where you have multiple robots that are working in parallel, or maybe even working with coordination with one another? That requires obviously a number of technologies that support multi-asset, multi-agent, multi-team, whatever you want to call it, things working in conjunction. And here we listed technologies where the focus is on the teaming aspects. There are many other technologies that would support any of these robots working independently, but focusing on the team is something that we think is important to then call out. In terms of supporting technologies, if you have multiple assets working together, maybe having some sort of cross-link surface communication is needed to support that, or even cooperative power sharing or distribution. There is obviously a lot of R&D here on Earth in multi-robot teams, things from robot soccer, a lot of DoD work. DARPA has a multi-swarm project, for example, called Offset, which might be relevant. I think that for us, the big problems is that the rough estimate of development costs is really, frankly, unknown, because the whole question of if you're building N robots, is that N times the cost of one robot in terms of building, deploying, and operating? Or is it cost more because of the greater complexity, or do you get some benefit of, quote, scale by creating more of the same thing? Anyway, that's the overall summary of multi-robots.
So building on Terry's slide about multi robots, we also consider the effect of adding multiple humans with multiple robots. And the key takeaway here is how to best capitalize on the fact that we have access to humans, whether they be on the surface of the moon, whether they be on a habitat, on Gateway, or even back on ISS, maybe back on Earth. Motivating example is this multi-site sampling area to accomplish one of the science objectives in the volcanic crater region of the Marias Hills, where we want to capitalize on our human assets to decrease risk of losing a vehicle or instruments in this region. Once again, that's going to use most of the same autonomy categories that Terry had for multiple robots, except now we're throwing humans in the mix. So not only do we get to estimate the state of a robot, we get to estimate the state of every human that we might need to be in contact with. What this will require is taking pages out of the POMDP book, where we're scheduling and planning with high-dimensional state spaces, with unknown models, uncertain actions, uncertain observations, and uncertainty in a shared belief. In particular, the idea of model mismatches, where the robot has a certain understanding of its state, a human has an understanding of their state, but how to make the two match and produce decisions regarding the other that might be potentially wrong, without failing and being able to accomplish the mission in the end. This will build on contemporary research in both human-robot teaming and belief state planning. This is an enhancing technology. We could perform this mission with a single robot with the traditional human control. The challenge there is going to take a lot longer. And by capitalizing on the multiple robot aspect of it and making better use of our humans, we can get our mission objectives complete in a much shorter period of time and without risking operational lifetime limitations of our robots. Our proposal is to leverage our current technology and include those focused technology programs through our university partners, potentially, to increase the TRL. We believe this will decrease the risk because we can make better use of the assets that we have, both human and robotic. Other things that we might need are going to be contemporary work in the areas of state estimation and human psychology to better understand the people that are going to be around us, that we have to treat people as more than complex, as more than just meat sacks that we command. Emerson, who's next?
And so the last part of our look at all the different ways that autonomy can impact lunar missions was focus on adaptive autonomy. Like Steve mentioned, we have these different states that need to be updated for various, changing performance parameters and the people that are going into it and everything else. And so that ties really nicely into this more machine learning aspect for, over long duration missions, how things are going to be slowly degrading as time goes on, and understanding how to best select your science objectives even. There's all sorts of other places that as you slowly build up this data set in situ, you can leverage it and learn and improve the quality of your mission as you go along. There's all sorts of other applications as well in terms of allowing out-of-comm navigation that performs based on learned in-comm behaviors. If you think, okay, our drivers are more cautious maybe than necessarily was programmed into driving when you have a human in the loop. Hopefully that's something that your autonomous driving can pick up on and use over and over to help buy down your risk and improve your survivability. There also is all sorts of other, improve your baseline, have your system model track back to it, and develop baselines of the humans that are in the loop as well. That's not something that you can just program in usually. And if you program it in, I guarantee you that you're not going to do it right because people are messy sometimes. There's a lot of limitations, definitely, for being able to implement this machine learning on a rover, particularly computing power and picking a particular machine learning architecture that you want to use. But luckily, there's all sorts of research that's being done in this space on Earth that hopefully we'll be able to leverage for both public and private communities development. I'm sure that there's anybody would love to slap their sticker on the side of a rover and have it be, a partnership with Uber or somewhere else of, we helped teach the rover how to drive or help teach it how to avoid this or that or anything else. There's all sorts of risk reduction, obviously, that goes into this learning technology, and hopefully it will be served to enhance missions in a variety of different ways in the future. Any different activity that a rover has to perform, whether it's your want-to-haves, your science objectives, or your have-to-haves, like your survivability, if you can learn as you go, it will enhance the mission overall.
Great. Okay, brilliant. Here's the thing. You guys got a couple of minutes left, and which is great because the way it's going to work is if you, I'm just watching the clock, if you don't use all your 15 minutes, we'll allow Q&A. I'm not chewing into your time right now for that because if you want to walk away with the illusion of unchallenged brilliance, just use up all your time. I will point out, not only is this content great, and I think we'll have some Q&A that will reflect that, but these guys clearly finished early. They did the whole lunar logo on the top right there, color matched, so well done. Okay, Q&A for a couple of minutes, and then we're on to the next. Here, we'll have to quickly shunt around mics. I'm going to let each team worry about moving the mics around, okay?
So nice job, lots of detail, really interesting. But I think I heard that your two DRMs are wide area sampling and Polar Explorer. For what reason? Is there a science driver? If so, what? Is this for ISRU? What's the motivation?
So for those two in particular, there's a ton of different options and different missions that you can do. Those two type of missions kind of capture a lot of different areas where you can use autonomy. So another one that we didn't really specify was putting out the seismic network. That is something that.
These two, why these two? What science would you get?
So for the science for a Polar Explorer would be to look for volatiles and kind of map out volatile content. Not only are there volatiles, but what state they're in and how you can actually use them for ISRU. For the wide area sampler, that is there to characterize a given site or a region of the moon. In particular, the focus was on Marius Hills region, which is a volcanic complex. And so there are a bunch of different cones, and you could kind of use a team of robots to kind of characterize that site. So those were two of the reasons why, or a couple of reasons why we chose those two.
I was just going to add that in terms of wide area sample return from South Pole, Aitken Basin is one of the highest priorities in the current decadal. And the question there is whether or not you believe the Moonrise sampling strategy is the right one versus wide area sampling.
I just had a brief comment. Doesn't pretty much almost everything you said here also apply to Mars?
Yes, yes.
So what about telerobotics? Have you guys looked at that?
Telerobotics?
Yeah, telerobotics, because the moon's pretty close. So have you looked at? I know that. Even with autonomy, you still can do telerobotics, right? Can you
Yeah,
not?
you could, on the near side, easily do telerobotics, sliding autonomy, basically kind of figuring out, getting some information back. But the idea behind this is there's a lot more information than you're going to be able to downlink while you're in motion. And this isn't supposed to be a slow-moving rover. This is supposed to be one that keeps moving over rough terrain. And so you might not be able to downlink everything during those periods. And so...
Okay, and so I know that one of the biggest things that people are considering is survive the night, the lunar night. So did you guys discuss any of that?
We did discuss that. So one of our topics was if we were relying on solar power to do the sun synchronous roving across, RTG does kind of negate that. So it's kind of an option. Yeah, so if you want to fill out the paperwork and go through that process, you can get an RTG and you won't have to worry about as much about surviving the night. But if you do, then the sun synchronous roving might work out better for you.
Okay, we're going to have to call it there. All right, brilliant. Thank you, Team Moon. That was excellent. So we're going to move past small bodies for this moment because I saw Isa came in, but I don't have the slides yet. Pat is next with Venus. You guys all did artwork. We gave you too much time.
We had a wonderful grad student that did artwork. So the team is the same team that I showed yesterday. I should tell you that the autonomy folks on this are Lorraine. She's really an AI person, and Rebecca is the graduate student, but she is also in autonomy. She's at Caltech now. So and Michelle works a lot on TRN. So there was. That we did have, despite what actually is on the chart, there is actually autonomy folks in this team. The team was really coherent. Unfortunately, Darby had to leave, so our science lead had to leave. Where's the clicker? Is this?
You can do that or hit the arrow.
Is this
You may, yeah. Just click that.
okay. So the science questions, they didn't change from yesterday. Venus's early evolution, including possible habitability and the evolutionary paths of Earth-sized terrestrial exoplanets, atmospheric dynamics, composition and climate history, and how physical and chemical processes interact to shape the modern surface of Venus. So yes, we did do graphics. Thanks, Becca. So the idea was, so we had two DRMs. One DRM was essentially a pathfinder for the second one, but it really covered a lot of the autonomy in a simpler form than you would use in the more complex form that I'll show second. So this had an orbiter, some CubeSats, an aerial vehicle that had drop zones, and a landed surface vehicle. Probably was not long-lived at all, but would last long enough to do some experiments. So we actually filled out the form. So I'm going to go through this. It's a little tedious because it's a lot of detail here. But the idea was to characterize Venus' interior surface and atmosphere. This is the dates we picked, by the way, were the decadal survey dates. So we picked the next decade, and then we picked the decade after that. So the idea was to try and phase these in terms of how you could actually get the autonomy into a system and work there. So the first one was describing the reference mission, and that was characterizing Venus' interior, surface, and atmosphere while demonstrated increasing autonomy. And it comprised an orbiter and small sats, and the science you can read up above. An area vehicle that would get into around 50 to 60 kilometers at this point, where there's a benign environment. Having dropsondes to acquire pressure, temperature, chemistry, wind velocity in the atmosphere, and then the landed system, looking at rock types and mineralogy. So there's quite a lot of science involved in this particular one. So in our lingo, testing autonomy, it's survive, detect, and communicate. So this was the initial stages with the lander system networked with orbiter and area vehicles, dropsondes. So everything was connected. But we wanted to demonstrate autonomous navigation of aerial vehicles and test techniques for measuring the altitude and the attitude. So the things that we'd need are fail operational algorithms and models for hardware degradation under Venus conditions, sensors for dropsondes. There's a lot of technology needed in all of these areas. But again, in some sense, it reminds me of the Earth and probably what Mars could do in terms of the autonomy, multi-agent autonomy was really the core of all of this. We wanted to test the architecture for communications and navigation capabilities, and looking at the mechanical systems. I'm sorry, I dropped down one. So demonstrating individual situational awareness and adaptability and planning, scheduling, smart execution and resource management algorithms. How do you actually do these things in these types of environments with multi-agents that have different capabilities of compute power on board, ranging from very little on the surface to very little on the sondes, but increasing as you went up to the orbiter. So each of these has a different capability, and how do you manage all those resources and decide on what science can be done within the whole ecosystem, if you will. Anything that we need supporting is flight hardware and sensors, test architecture we wanted to look at communication navigation capabilities. We weren't quite sure that we actually knew how to do this at this point. Mechanical systems to control altitude of aerial vehicles. And one of the things that really needs to get done before any of this happens is we really need theoretical models. 93 bars of CO2 is really a fluid. And we actually, with winds and with things that are moving, we actually don't know what that's really like. So before we do anything, we actually have to know that. And this is a very fundamental theoretical model that we need to develop of what it's like to be at the surface of Venus or even 10 kilometers up. There's several related projects going on. LISI is a Glenn Research Center. I don't know what you'd call it. I guess it's a study for
long-lived lander.
Long-lived, but it's a study, right?
It's not a study. It's a project. It's a hardware development.
Oh, it's okay. It's an actual pre-project. Okay. Okay. So we have that in the works right now. It may or may not be ready in this particular time frame, but it may be. Venus aerial platforms need some work. And the planetary aerial vehicles. So a lot of the publications there. Enabling or enhancing for enabling or enhancing for autonomy. Enabling and enhancing, in this case, some of it is enabling and some of it is enhancing. And so the demonstrating the autonomous systems technology in the harsh environments is enhancing, but the atmospheric science is really enabled by these small sats and dropsondes. So there's quite a bit that actually is enabled by autonomy in this particular case. And this will require what we felt was sort of the equivalent of development costs of a new frontiers. Maybe that's a little ambitious. So on to the next one. This one is more elaborate and has more agents, more assets, many more assets on the surface. They would be long-lived landers, so much more ambitious. Again, we'd have the aero vehicles at around 50, 60 kilometers nominal, but they could now go up and down a lot more. So they could come down to around 20 kilometers up to 70. So there'll be a lot more diversion, a lot more control of the altitude. And many more CubeSats, small sats to investigate the higher altitudes and correspond with the aerobots in controlling where everything goes. And then the overarching, up the top, you'll see the overarching orbiter. And we filled this out in gory detail. So I'm going to just, this is really, we thought this was supposed to be filled out. So we did. So, but the role, this one is particularly a focus on volcanic eruptions caused by volcanic plumes. Maybe I'll read from here. And releasing clouds of volatile. So this is really now looking at not just the atmosphere and the static measurements that you would do in the previous one, but is now relying on serendipity to find the volcanoes and actual, what can we see on the surface happening that we want to reorient everything into the environment. So this was much more difficult, in fact, in terms of autonomy and how you'd actually do all of these things. And of course, you know, if we can find seismic events, again, the same thing, we'd be moving things around. You can read the details. They're very similar in terms of the needs. A lot more autonomy technologies are needed for this. One of the things that we think fairly straightforward to do, but needs to get done, is terrain relative navigation and hazard avoidance and station keeping capability. So that is something. We know how to do it for Mars, but we don't know how to do it for Venus, because you wouldn't necessarily have visual maps until at least you got down below 10 kilometers and maybe not know exactly where you're headed until that time. So it's using multi sources of background to get to the navigation scenarios. Controlling drop zones, how do you do that? Through these dense, rapidly moving atmosphere. The atmosphere moves much faster than the body itself, so you want to make sure that you know how to control these zones, or do you just drop them off and have them be able to find what you're looking for on the surface. Sensors and controller of drop zones, communication across multiple platforms again, and again, situational awareness and rapid response. So that's the list of the core autonomy connections that we'd need, autonomy technologies we'd need. With the supporting technologies, now we need to be much more aware of the harsh environments on the surface. And so this is where you really need to be able to do the high temperature electronics, get the somewhat better possible compute systems on the surface, and so on. So this is what where we're headed in this area. We filled this out, but it was very similar to the other chart, except turned around. On the other hand, the one column that is different is the last one, which is the current state-of-the-art projects and products. We feel that a lot is done in the Earth application, whereas Mike Little, a lot of it is. Yeah, it's looking at, I think, things that you're looking at, sensor webs, and I think a lot of the technologies in the autonomy area could be at least transferable, and this is possibly true of Mars. I don't know what the Mars DRM was, but that may be well true of that one as well. So I think looking across, so the other message I have is looking across the DRMs to see what could be done across the DRMs is really important too. Ours is a special case because of the atmosphere and the temperatures and all the rest of the things, but looking across the DRMs I think is quite valuable, and that means it really is at the SMD level, not the individual divisions within SMD. And again, this is very similar. We did take a look to see whether we actually responded to the question of white paper. And we decided that a white paper title would be Designing for Autonomy on Venus: Survive, Detect, Communicate, Coordinate, and Respond. And we'd cover the topics that would be in the DRMs that we just discussed. So that was the notion of how we'd go about doing a paper in this, or a white paper in this area. And we did try and go back and say, okay, did we answer your questions on the front page that we were told to remove? So we did look at this, and the scenarios that demand autonomy include, but are not restricted to, constrained communications with Earth and among assets on Venus, time-critical decisions involving events such as lifetime constraints, Venus quakes and volcanic eruptions, internally data-heavy decisions such as TRN, onboard data analysis and processing. A lot of either the radar or even the infrasound require quite a bit of data processing on board and between the assets. So you'd actually like to consider intra-data analysis, not just data analysis or data back to Earth. System architecture simplification through independent decision-making and situational complexity that exceeds the limits of useful human input, such as responding to surface events or changing atmospheric conditions. For example, the aerial assets are moving at 5,600 kilometers a day, so that's quite a bit. So with that, that's it. That's my spectrometer.
Trish, Pat, that was excellent. I have to say, I think Florence, I'll hazard a guess, that's the kind of level of detail. I saw you nodding a lot, so I know you're.
It's awful to give the talk.
No, it's excellent. I mean, this is.
Needs to speak up. So if any questions.
Yeah, we have time probably for one, maybe two questions. Anyone got a question? Yeah. Did you have one? Oh, sorry, I thought you put your hand up. Anybody? Okay. Oh, we have one at the back.
Quick note. Knowing it's a harsh environment, do you have any need for instrument prognostic or diagnostic capabilities so they can protect your assets?
Yes, yeah.
Hold on one sec, I'll get you the mic.
Yeah. Yes.
That's it. Okay, that was not worth the mic. Okay, we have one question, and then.
I was going to try to help with that answer.
Okay, move that down to the corner quickly, and we'll get on with the next one. That was great.
So in the shorter term, for something like LISI, which is supposed to show proof of concept by 2021, you would have basic sensor systems. As you go towards the time frame that you're talking here, in the harsh environment area, you might wish to have both health management capabilities for the vehicle, as well as capabilities associated with health management, diagnostic, prognostics, associated with the instrumentation. So the idea that you might transfer, in a sense, some of the capabilities that you might want to have in room temperature, ambient temperature vehicles towards the high temperature arena, the same problems exist, the same need to understand whether your system's falling apart or operating properly exist. The problem and challenge will be is to transfer those capabilities to harsh environment applications. Does that answer your question?
Yeah, it's over, yeah. I think we have to move on. I'm sorry, if you have other questions, though, do shoot them over to Pat, because otherwise we'll run really late.
It was just a further clarification. I think Gary was...
No worries. It's okay.
Gary was talking about the long-duration surface systems. Mm-hmm. I think the problem there is unique. The problem is more severe. And with the orbital assets, we have no such problem. And with the aerial platforms, they're operating at Earth environmental conditions. They have to contend with sulfuric acid mist, but they don't have the same problems that Gary was referring to here.
Got it.
He was quite correct.
Okay. Sorry if I seem draconian with the timing, but what I'm very cognizant of is the AUV demo, which is scheduled to take place. I want to make sure you all have a chance for that. Next up is Mars, who is running the show.
We're sharing it.
Okay, very good. Let me start the timer for you, and you are good.
Okay. So both Eric and I are going to explain some of this.
You can use the arrow.
Okay, great. So our group went through our science mission objectives. This is our starting point. I've kind of recapped. This is just a recap of what I've previously told you. But we're going after subsurface water and trying to understand what it is, what its composition is, how it got there. Has it melted? It's currently ice. Has it melted at some point, such as during high obliquity in the northern plains or something like that? Is there life in it? It's a really important question on so many fronts. And we kind of combined in with this the idea of monitoring weather conditions. And despite this being a very science-oriented set of objectives, we recognize that The results of this would be applicable to human exploration as well, in the sense of understanding accessible water for future ISRU, as well as the meteorological data feeding into human habitation. So our payload, like I said, we went through and tried to think through what this mission would look like before we added the autonomy. Our payload essentially consists of a fleet of rovers that have the capability to drill into the subsurface, probably about 5 meters. That's a TBR. And look at the general composition of it in terms of what kind of water is present. Is it free water, or is it in terms of ice, or is it hydrated minerals? Look at some of the composition. Have the ability to take a sample and deliver it to what we're calling the mothership, which at this point has been defined as a larger rover which has a laboratory involved in place. All of these little rovers would have weather stations included on them, and imagers for detecting features, navigating. They would all have the capability of communicating with other surface spacecraft and orbiters, and the fleet would have a wide area wireless network capabilities with delay tolerant networking, which was scalable. And I'm going to let Eric talk about that shortly. There's a mother. Well, it's one of our autonomy. It's listed in our autonomy stuff. So I'm gonna let Eric talk about them. The mothership has the capability of detecting biosignatures, receiving samples. It would have powerful science data processor. This is really key to the science return of the mission. And again, that is it enables the autonomy on the science side. So. Again, I'm going to pass that over to Eric in a moment. The mothership would also have robust communication capabilities between Earth and Mars, and also among the rovers and orbiters. So you see we have this different types of connections here for the different spacecraft. And then we considered a potential trade, which would be the introduction of helicopters for terrain and geological mapping, and possibly other additional weather measurements if we made a case for it. In dealing with the 3 big questions we were asked to address, what we decided was that what we're really talking about is infrastructure scalability, which is spatially, mission extendability with time, and extensibility to other missions, which is really this integration and growth of our fleet. In other words, we have this idea of our DRM, but one of the key values of it is that it could lead to all of these things in the future. And one of the things that, this is sort of like the bonus thing that we're adding in, thinking bolder. if the payload elements of the rovers, all of them, the little ones and the big one, had some kind of a standard form factor for its payload, meaning unit size, power, interface, maybe even the language it's using to communicate. This would enable future servicing and upgrading by other robots, which could be done autonomously, which means that we could actually support a broader range of contributed instruments and different types of science in the future. The other thing that we were thinking was that this type of DRM would enable us to expand our computing and network environments to multiple nodes. So you could add more rovers later, and also expand data storage environment. We went through and talked about some assumptions. In the interest of time, I'm going to keep going. Our key messages. While the steps in the mission architecture could be done without autonomy today, autonomy introduces high efficiency such that it transforms our exploration paradigm. How we do this mission would be, how we do science with autonomy would be completely different than what we're used to. And as a result, we would get orders of magnitude more science return. So yes, we can do a lot of this stuff without autonomy, but it's going to take a long, long time, and it's not going to come out the same. Is autonomy critical? In light of how we have structured the science objectives and what we want to achieve, yes, it is. Most of the science-specific autonomy capabilities do not yet exist today and need to be developed. And our DRM architecture will enable extensibility, which is I'm repeating that, but it's an important aspect. Some notes to NASA, we'll go back to those later. I'm going to pass it off to Eric to talk about individual autonomy capabilities.
Okay. Yeah, so we didn't quite complete our homework, but let me go over, our kind of mission design. So we're imagining multiple rovers on the surface of Mars. We're thinking 4 or so. One of the mission objectives on page 1 was to cover a 100-kilometer radius area and investigate that. That number was chosen because that's for a human mission to Mars. That's the standard exploration zone we're talking about. So we picked that number. If you want to do that, you need a lot of rovers, and they need to move fast. So that's the context. We have 4 rovers. We have another rover, which a bigger one. Most of these rovers are very small, which are lightweight, able to communicate with space. There's one big rover. Maybe it has a much better chemistry station on it. The small rovers can bring it samples. There's also an orbiter with our supercomputer on it, some sort of powerful computer. The rovers can actually send their data up directly to this thing and ask it to do processing maybe, and come back down. So I was put that all in context when we talk about these 4 particular elements of autonomy that we identified. So are we already over time?
No, you're good. You got 7 minutes.
Okay. So the first one was individual agent task planning. So this is each individual rover's job. At some point, something's going to tell that rover, we want you to go to this grid square here, find a good place to analyze, to drill, to look for the water, and then go do that. So that's this individual agent task management. So we broke that down. The things it has to do is it has to have some sort of remote sensing. It's not giving a pinpoint, don't go to this exact location. It's just go to this general location. It's going to scan with some sort of subsurface scanning, pick a place under there, underground, and say that's a likely place for water, for what we want to do. And then it's got to approach that and get the sample. It's got to make these decisions all on its own where to drill, and combine the remote sensing of the whatever subsurface sensing we have and image sensing to pick this place. So that's one of our autonomy items. The items in red we have on row D there are the things we think aren't really doable today. So some of the things we need this.
Quick, so in your scenario, the human provides goal. Is that correct? You use passive voice. I'm not.
I'm going to go on the next task we have is going to be the multi-agent planner.
Okay.
So this guy is going to decide where each rover goes.
Okay.
An important aspect of what we kind of assumed on all of this was that the tactical planning, which is really, activity planning, activity sets of things are all autonomous. But a long-term plan would actually involve humans in the loop. So something bigger than just a set of activities would still involve humans in the loop. So we didn't take humans out completely. It's just that, on MSL, we have a drilling campaign. It takes 3 weeks. That could be, autonomous. But, where do we want to drill? That might be something that, on MSL, we would still consider that's long-term planning. In this case, we have to be able to address some of the data, look at the data. Is it being interpreted the way we think it's being interpreted, and maybe provide some further direction on what the next steps would be?
So, yeah, the question was simply, thank you. You say science event detection and response. Is that your rover is detecting something by itself and responding by itself, or is it detecting something and telling the humans, I found something?
It's detecting it by itself. So our concept was, it's told to go to some general area and do analysis. If it sees something on the way, it would stop and do something there.
That was my
or if we had this example of if it looks around and sees something unusual on the ground, it's like, whoa, this is interesting. I'm going to stop here and start studying. Our idea was to get rid of the tactical team and get it so the scientists can just say, I want to do this in general. Okay, a couple of important points here. So we have the in situ subsurface structure remote sensing at the rover scale for integration into what we call a DTGM, a digital terrain and geology map. So, and we're going to make actually a 3D map of the subsurface and keep that going. It's going to upload that information to our master computer in the cloud, literally in space, the orbiting computer resource, where a map is maintained and continually added to. So at the beginning, it doesn't know that much, but it's going to keep adding to that map. So the scientists will start to see underground structures and how they're all connected as this mission spreads out. Another one is the onboard spectral analysis for mineralogical content. So this is an important one. Once we get whatever instrument we have, looking at the composition, looking at the mineralogy, it's going to have to make a decision and say what that is. Water. Looking for the water. Also the mineral. And okay. It's going to have to come up with a decision. It's like, yes, there's water, and it's like this. And not just send back spectra. It's got to look at the spectra and come up with like a clear, easy choice to tell the mothership and to put in the map. And then onboard an interest operator to analyze, prioritize, and decide the next activity, especially when transients happens. So it looks at this and says, I didn't see water. Should I go drill over there, or should I drill deeper, or what should I do? Based on what it had, make a reaction to that. Okay, so that's the rover's individual agent task planner autonomy. We also have the collaborative multi-agent task planner. So now this is maybe something running on the orbiter, or on we're calling the mothership, the big rover on the ground that has like a lab in it. It's going to decide amongst all these rovers, you go over there and you go over there, kind of coordinate the whole thing and look at the big picture, and then send the commands to the rovers to do their thing. What grid square should they go, and what should they look for there? And the key components of this, delay tolerant networking. So all the units on the ground are going to be able to send their data, and it'll eventually it might transfer from one rover to another, or it'll find its way back to the mothership, back to the master computer. Mesh networking, peer-to-peer. We want peer-to-peer interface standards for multiple interacting agents. So we want like a standard here. We want to be able to send another rover, maybe a completely different instrumentation on it later, maybe. We really want to have some sort of standard communication protocol, not just invent something for this mission. And again, we need high-performance remote computing. Okay, the third one, I'm sorry, I have 1 minute. Sample acquisition and delivery. So we actually broke down the drilling activity is complicated. So we just broke this its own autonomous thing. The rover, when it gets to the place, it identifies, it's looked under the surface, identified, I want to drill right there. It's got to maneuver to that place, get the drill in position. The drill's a tricky thing. We're talking about a drill that can go 5 meters maybe, and it's going to weigh like 2 kilograms. So you want to control that drill carefully, and we decided that this itself was an autonomous thing. It wasn't just automation, but it's complicated enough to be called autonomy. And additionally, we have to bring that sample up and do something with it, and we're thinking of like maybe we put it in a container that we can deliver back to the mothership. So all of that is another autonomous thing. I'm running out of time. So the last thing we had was navigation. So there is autonomous navigation where we have the motherships come up with this plan, and it goes and tells each rover, you go from point A to point B, and that's the rover's job to autonomously navigate across that. So using the mapping that it's learned from all the other rovers. And we can do that. Maybe the first time it traverses a route, it doesn't know much about it, but it's mapped that. Or another rover's mapped it. So it'll get that map, and it can, as the more often it travels that route, the faster it can go. So we can make this traverse more and more efficient. So, okay.
Thank you. That's great. I know it's tough to get through all this material. Fortunately, we don't have any more. We did some Q&A midstream. We don't have time for more right now, but you guys all know how to reach out to each other. You know what's going on. So next up, we're going to do Helio. So I guess Larry, if you're, or Mark, or both of you, I'm not sure who's going to present. Okay, do your thing.
Great, thank you. So I'm the Helio rep, Larry Kepko. We had George Ho and Mark Chung. We're the three of us working within the Earth Sciences. You can see I added a picture. That's Matt Damon sitting on Mars. The goal of this autonomy mission is to protect him or whoever we send to Mars. Okay, next slide, please. Or just
sure.
click.
You can use the arrow.
Okay. All right, so there is a need in the coming years to safeguard human exploration throughout the inner heliosphere. Right, something called space weather. Space weather can be quite deadly. Back in 1972, there was a very large solar flare in between Apollo missions. And we've gone back and looked, and we figured out that if an astronaut had been on the surface of the moon during that flare, they would have received 400 rem of radiation, which is a lot of radiation to receive, and that's not good. And they had no indication this flare was coming. We don't want that to happen. If we're going to have astronauts on the moon, on Mars, on asteroids, doing activity in space, we need to protect them. And we need to know when a flare is coming, how big that flare is going to be. So the concept here on the left is a little cartoon showing the sun in the middle and a network of satellites. You can have them out at Earth orbit. These are imaging satellites. You can also have, you really want some further in, closer to maybe Venus. It's not a flag planted on the sun. That is over the sun. Right. So you want satellites over the sun to look down, because one of the big gaps is the coronal field, the polar coronal field. It's a big gap right now. We actually never observed it. And then we have spacecraft that are on here at the inner orbits where they're actually monitoring the solar wind before it hits the Earth and gives us a lead time. You also know if we have people on Mars, that sometimes Mars is on the opposite side of the sun. And we may not actually be able to talk to them except through relays. So that's a bit of a problem. Kind of things we're talking about are EUV imagers. So if you've seen any picture of the sun in the last couple of years, it's probably from SDO. SDO produces 1.5 terabytes of data per day. It has a dedicated ground station just for that spacecraft. If we've got, say, a dozen of those satellites around the sun, we're not downlinking all that data, right? We need to figure out how to process that data onboard the spacecraft, pull out what's important, and send only that important detail to the astronauts. The other thing we have, so that's on the upper left of this side. So there's an EUV imager. You want to have a little cutout, and it's looking at that little active region where the flare is occurring. And understanding it in real time, trying to make predictions of whether it's going to see a flare or not using machine learning. Because every flare and every active region actually turns out to be very different. On the upper right is I guess a drawing of a coronagraph. Have you ever seen the big explosions come off the sun, a coronal mass ejection? What we usually do is we use something like SOHO or stereo, and we pull those images down to Earth, and then somebody down the hall from me looks at those images and say, well, this CME is moving this fast and it's going to hit the Earth at this time. That's one spacecraft. What you really want, and what stereo tried to do, is have tomography. And again, if you're thinking about these kinds of images you're producing, you have a bunch of spacecraft around the sun. Trying to do tomography by sending all that data down, do it on the Earth, and then send it back out is too intensive. You really want the spacecraft to communicate with each other and do the tomography on orbit and figure out how that works, and then just send us that there's a CME on the way, and it's coming in a day and a half, and you better get back inside your shelter. The other thing we have are vector magnetographs, a lot of data processing, very data intensive. A lot of that could be done on the spacecraft as well. And then finally, LV in situ, which is actually the low data rate stuff that I study, magnetic field and particle detectors. What you want to do is have this whole network examine all these data, take what's coming, and then send that out as a blast to the network, right? And say, all the astronauts that are out there, you're about to get hit with a flare, you've got about 12 hours, 5 minutes, whatever the number is, get back in your shelter, get back in your spacecraft. Right, this is about protecting human exploration. There's a strong need for this. All right, so we did our attempt to fill this out. I would say this has less robot autonomy than some of the other things we're talking about. There's a lot of machine learning here, which I know isn't quite autonomy. There's automation here. There's a lot of AI here. I'm not going to go into a lot of detail. I think I did that on the previous imagery, but a lot of it is trying to look at all this imagery that it's getting on the surface of the sun, maybe directing new assets. So one thing, if you look at SDO is a full disk image. The resolution actually isn't that great just because there's so much data to send down. So you really want our larger spacecraft that can focus in like a little straw, a little microscope. And these spacecraft should be able to tell that larger spacecraft, point at this region, and analyze those data for us. So spacecraft controlling other spacecraft. I think I probably talked about all this stuff. I'm going to try to get us back on time here. We have two candidate white papers. One is the Autonomous Space Weather Network that safeguards human exploration of the solar system, the beginnings of an abstract. And the second one, we didn't spend a lot of time talking about it, something called Interstellar Probe. That mission's been on the books for decades. We've always wanted to do it. This is a mission to go out to 1,000 AU, traveling at 50 AU per year, I believe. Just to give you a perspective, Voyager is traveling at 4 AU per year. So you need to travel really, really fast to get out there. You can imagine the kinds of things that you might need. If it takes 5 days or longer to talk to that spacecraft needs some autonomy. And if something goes wrong in that spacecraft, it needs to figure out what went wrong and how to fix it. There's a whole team at APL studying this with, I think, some headquarters money. So I think we'll probably do a white paper on that as well. Very different than the kind of thing I talked about before, but those are our two papers that we have, and I think that's
it.
all
Well,
I had. Yeah.
time for questions. And I'm going to start by saying I think you did us a real favor by commenting on something. You said autonomy doesn't necessarily mean robotics.
Right.
It doesn't have to mean actuators and physical things happening. Autonomy can mean attention setting. If there's uplink, downlink issues, what are you going to focus on? And you better get it right. I completely agree. We have time for questions for sure for the Helio team. Any questions?
Helio is less accessible than Mars and Venus, right?
Okay, that's cool. Thank you very much. Appreciate the presentation. Well done, guys. Okay. Okay, thank you. Appreciate it. Good job. Next up, we have Rudra with the ISA. Did I get this? Yeah, that's your guy.
Can you see the Excel spreadsheet first?
Sure.
All right, good afternoon. So in my head, as long as yesterday was, with the diversity of thoughts that we heard about, today felt like it went in a blimp because of the cohesive discussions in the DRM sessions that we had. The 4 hours just disappeared. So if you look at our slides, they're not quite all there. For some reason, I didn't get that slide package. Maybe it was my internet or my phone or my computer. We didn't have that template. So it's not as filled out. But we had a very lively discussion for the time that we were allocated. And so let's walk through the process of how we used our time. One thing we did was, we have a very clear DRM with a clear objective of, building this 20-meter telescope autonomously in cislunar environment and operating it in Sun Earth L2. And that's a very, clear, these are the things that we're going to do. We had a clear definition of what the modules look like and so forth. So the first order of business that we did was went through the taxonomy. It's a great start and has a fair amount of granularity into what autonomy actually means. And we listed in red, yellow, and green what were the critical components, red being the most critical, and yellow and green being the lowest criticality of the component technologies towards achieving this DRM. And so we color-coded all of those, and then we asked what are the TRL levels in terms of maturity of each of those component technologies as it pertains to the DRM specifically, right? When you talk about sensing and perception, well, that's a broad area. We asked how does sensing and perception correlate to this DRM in particular, and then we listed them as a high, medium, and low. High meaning you are in TRL 6 through 9, medium meaning the value of death, and low meaning 1 through 3. And so if you see things in red and in low, those are critical things that we identified as technologies that we need to study more and discuss a little bit more and see how it impacts this DRM, particularly as it pertains to autonomy. So if we now slide back to the PowerPoint presentation. Okay, so before we get into the details of these slides, a few things stood out. One, we talked about what does autonomy and what does automation mean in terms of this DRM. And then we came to the conclusion, if you talk about autonomy, there is a long time autonomy. That means you pack all your fairings, send it up into space, and then something happens and you have a telescope working and you're doing science with it. But that's the long range autonomy that we thought about. And then we thought about short range autonomy, wherein the robot does specific behaviors and then you have human supervision to check for that. So it's a periodicity aspect of how often do you check for autonomy with the human in the loop, right? Within the perspective of the DRM, we talked about an autonomous. That means no human in terms of doing EVAs, but we talked about mixed autonomy with potential for supervised autonomy, and if there were human operators doing high bandwidth limited operations per se. So 3 clusters of technologies jumped out at us and said these are the things that we could do as elements that increase the state of art and facilitate this DRM. So let's talk about what were the challenges with this DRM. One, there is the aspect of bringing multiple agents together. So you have a fairing, you have a tug, and you have the assemblage and the robotic systems in there so that you can get all the lumber from the multiple launches in one place so that you can do assembly with it. Second is many deliberate, precise contact. Right? Anytime you have contacts by robotic systems autonomously, that's potentially an element for risk. And so handling those contacts deliberately and precisely and doing them safely and autonomously was a big challenge that stood out, and associated risks in those elements. The third aspect of it is you're building something in space, right? So you have to get this thing working. So the V&V aspects of it are very challenging, and how do you go about doing those? The fourth element part of it was sort of the trajectory and orbital mechanics aspects of it, because you're constructing something which has uncertainty in its modules. So you have center of mass uncertainties, you have a center of pressure uncertainty. You may have to move in terms of agility, in terms of orbital corrections and so forth. So those are a few of the things that jumped out and grabbed our attention. And so in terms of the clusters of technologies that we looked at, we created 3 slides that capture the essence of things that we thought were important to discuss in this forum. Now, I would like to make a point that these slides are not complete. We'll work on these in the next few days and get them to a point which captures all the discussions. We focused on using the face-to-face time in having discussions rather than writing this down. All right, so the first theme that came out is anomaly detection and fault mitigation. So in terms of what is the objective? Well, you're constructing something and you're going to move a lot of elements. You're going to deploy modules. You're going to assemble things. So if you have an anomalous situation where something that was supposed to be deployed didn't get deployed, right? Or you were doing you had a fault in the system, you were torquing something down and you had a torque exceeding a current limit and so forth. Now we do that today, right? We have telemetry or we have software that says if you exceeded the torque, stop. But I think when we talk about autonomy in the context of assembly, you want the robot to be able to decide for itself what exactly happened in terms of the anomaly. So the first order, when you're talking about short-term autonomy, that means there's an opportunity for the human to intercede at the end of the day or in the couple of days. While there, the objective is to do no harm. So you want to bring the system to a graceful stop so that the overall assemblage and the mission is not compromised, right? So the autonomy to decide what steps need to be immediately done so that if you're crushing something, you don't end up crushing it. If your torque exceeds, you don't go about doing it so that you crush it. In the same way, if you have a fault, then how do you discern in terms of why that fault was caused, right? If you have a long-term objective, like you say to the robot, go build the primary mirror, right? So a short-term example is you're placing each mirror module and the human can supervise that. If you say, robot, go build primary mirror, well, then if there's a fault in that process, the robot has to be able to gracefully back out of that first, and second, take mitigating steps towards that. So what are the technologies that enable it? Well, multi-sensor fusion is one aspect that jumps out. The discussion focused about sensor fusion from the classical sense to fusion of unconventional sensors. So if you have force-torque sensors, you have current sensors, you have cameras, LiDARs, metrology, and all those kinds of different sensors that we don't typically apply in unison today need to be fused together. And they may have their own challenges in terms of their bandwidth, in terms of the resolution at which you're talking with them, and so forth. The second aspect is, of course, state estimation and monitoring. Monitoring is more in this aspect. Now, when we talk about what are the other things that are going on that could help us, climb this hill, well, there's a lot of activity that is going on, one in space servicing, which is Restore L and RSGS. They are developing, these are missions that are potentially coming forward and might reduce the risk associated with these. And the tipping point activities that are going on, if they go to the phase 2 as a part of ORMA, we'll also see a lot of these deliberate contact-based activities and potentially, some of the anomaly detection aspects. And then when it comes to bringing multiple agents together in terms of RPO, XSS 11 is a perfect example of things that has been done in the past. And there's a lot of work that's going on in terms of bringing these servicing vehicles together. There's also the work that's going on in small sats and CubeSats coming together. So we felt that's another thing that's enabling this. All right, is this enabling or enhancing? We felt that this was enabling in nature because of the kind of DRM that we have stood up, right? You're going to do same kinds of behaviors multiple times. So the complexity is not in the specific behavior necessarily, but the fact that you're doing multiple of these, right? So statistically, there may be avenues where you have anomalies and you need to be able to mitigate those. And so we discriminated in terms of the short-term and long-term anomaly in here, and said if you had long-term anomaly, then this would be a significant thrust. The question was put, how much funding is potentially needed? We didn't want to put $23.6 million or whatever the number was. And we felt, is it $1 million, or tens of millions of dollars, hundreds of millions of dollars? And we felt that this was something in the order of tens of millions of dollars in technology development. I think for some reason it's getting cut. Okay, so what's the risk factor? Well, when we had a problem with the previous telescope, the cost of getting humans up there and doing the servicing on HST, that was quite significant. Yes, it enabled something that we had never done before. It was a triumph for humanity in some sense. But if you had to repeat that on a mission of a large telescope realization, that would be quite an extensive cost. The second aspect, which is I think the heart of in-space assembly in terms of robotics and in deliberate contacts and so forth, are autonomous maneuvers, mobility, and manipulation. So distinction, when we talk about mobility in this forum, you're talking about rovers. Here we're talking about mobility of a robot on a truss or an assemblage that it is working on. Right, so there's a difference in here. You're making and breaking contacts as you're moving over this assemblage that you're putting together. Maneuvers were orbital maneuvers. So if you have a fairing that's bringing you, your components, you might have to take a tug or a MEV or a servicer and grab onto it and take it to the assemblage that you're putting together. You may also have situations where you might have to be very agile and sort of move away from incoming obstacles and so forth. So we talked about that, and here is where we listed a whole bunch of technologies that can be enabling towards realizing this. So free flyer, autonomous RPO and berthing, robust truss walking. This is where you have deliberate contacts and so forth. Dexterous, forceful interactions and so forth. Manipulation of soft goods. When you're assembling instruments or you're servicing instruments, stray light becomes a big issue. And today, human beings touch a lot of elements. A lot of these mylar blankets, get put together, and it's a very intensive process on the ground. Realizing that in space is a big challenge, right? How do you ensure that you're able to manipulate these soft goods and still get stray light blocking? Handling of gossamer structures, you're making this so that you're able to save on cost and risk, so your structures are fairly light. It's been designed for operation in space and not on the ground and so forth. Managing the overall stack in terms of spacecraft control in a distributed sense, if you will, distributed actuation, distributed sensing, and distributed control, because as you're building this thing, the center of mass of the system is moving on. And again, the point being, we can learn a lot from the upcoming missions. There may be opportunities in learning and adaptation, particularly as the system has deliberate contact. So as it makes many, many contacts, it probably learns what are the bounds in which it stays in. If you have drift in calibration, for example, in your sensors, you may be able to learn that you're drifting and be able to calibrate and so forth. There are a fair number of activities that are going on in the DoD, in the commercial world, in multi-agent systems that may be able to contribute towards developing or reducing the risk associated with this effort. This is again an enabling activity in terms of the DRM. If you're not able to make those contacts, if you're not able to get elements to assemble together safely and repeatedly, you're not going to be able to assemble the system, right? The cost again came down to, what is the cost of reducing the risk in developing this technology? We felt collectively that it was again in the order of tens of millions and not hundreds and billions of dollars. What's not showing over here is a comment that said we wanted to do this in terms of incremental system level demonstrations because of the complexity is in number of iterations rather than one behavior. So ground demonstrations, demonstrations in lower Earth with CubeSats, small sats, maybe the gateway could be a forum and so forth. And then and finally, perhaps the most important topic that we got discussed, where's Josh? Josh came in here and he was a big champion for this, is autonomous VNV. So in-space VNV. We know how important VNV is on the ground. We're not going to be able to assemble this whole thing on the ground and then show it works, right? So you have to take this up into space, assemble it together, and then certify that the telescope is working just fine. So VNV becomes a big issue in this story. And I want to focus your point, which says, that's not really something that we've done a lot of, right? And so that was something that came up, that in-space VNV of autonomous assembly and servicing is a fairly new area with a sparse set of projects, if any. So that's an area of growth. What enables it? Well, we need new sensors, so multifunctional materials perhaps, materials that have strain gauges embedded as a function of them being realized, different kinds of actuators, limit switches that are miniaturized and so forth. Sensor fusion, again, of diverse and disparate sets of sensors and not the conventional set that we're used to. This concept of sense making, right? As a robot is doing its behaviors, you want the robot to be aware of what it is doing. Development of behaviors and protocols for confidence building in terms of VNV. Those are the kinds of things that come up. Non-destructive evaluation is a huge field on the ground, right? We do that extensively. How do we do that in space? And then finally, somebody brought up a point that we've been assembling telescopes on the ground for a while. And as I understand it, that process has become fairly efficient, right? So what are the lessons that we can learn from there and take it to space so that there may be opportunities for collaboration there? Again, the behaviors maybe order tens of millions of dollars, and again, those numbers are much debatable. It reduces significant risk in the performance, right? If you have a strong VNV approach, that's essential. And then I think my notes are mixed up here. Maybe. All right, we'll stop there. So those were sort of the things that we talked about in this the breakout sessions. And anybody in the team that has any points that they would like to make? Peter, Josh, Jonathan.
I think we identified a whole. You're going to need a mic. So I'm going to. You bought a little bit of time because I'm going to switch over to Mike's slides so we can do the next one. But if you have one more comment, just come and grab a mic.
We identified a whole slew of white paper topics.
Oh yes, that's
that we identified, and that was about.
Right, we ran out of time, so I'm not going to get into that. And we listed like 10, 12 topics for white paper that we can get into, and it can keep growing, right? But I think they are all cohesive in nature. So they're one major bullet point with many bullet points underneath. And I think the topic that came up, why do we need humans and why not do it with EVA came up, and then safety was one element that we identified. That the way the modules are structured, the smallest module is about 5 meters in size. So as you think of it, it's going to be a big challenge for humans to assemble it. All right, thank you.
Good job. Bear with me.
While you're doing that, so
go ahead.
So the investment that you had order of $10 million per DRM. Is that mostly in algorithms?
So we'll have recommendations in the slides, but some of them were algorithms, some of them were sensor developments, and some of them were demonstrations. I think in this area, particularly seeing is believing.
So there's a need for technology demonstration missions, you're saying, that only there's an aspect of this that can only be done in space to prove the technologies.
Yeah, so we felt it was staged. There are things that you can do on the ground. Then you can take them to lower Earth, either on the ISS or on free flyers, and then you could go out deeper where some of the communication challenges might come out. But again, as I mentioned, it's a number of things that you have to do and do them time and time again. So it's okay to say, can we pick this up? Yes, we can pick this up. Can you pick this up 100 times under varying conditions? That's basically the challenge.
Okay, next up is Earth. Let's get the screen back up again, and then thank you. Well done. Let's get Mike rolling. Wow, that's a big team.
Wow.
Yeah. So I want to start by thanking everybody on the team, and in particular, and I never do names right, but I can see at least one of them in front, two of them in front of me, are grad student scribes and reporters. They did a great job, and I've looked briefly at the notes, and that sort of helped me organize this. The team was pretty big, and but it was a collection of very talented and insightful people who had given a lot of thought to some of the work that we're trying to do here, and so they came prepared. Maybe I should say loaded for bear, Jason. But it was a very productive meeting. Like my predecessor, we spent most of the time talking about things, so as a result, I did the slides starting with whoever was first in the presentation. So they're not completely finished, but they'll be finished in the next day or so. So we had, you can see, we had a few DRMs that we had started out with, and we worked our way through settling on which one we really wanted to develop more fully in this conversation, and we decided to take the one that was model-driven observing strategy. So very quickly, what this refers to is you have models that run, for example, weather prediction model or hydrology model or an iceberg prediction model, and these are operational models. You want to, the weather forecasting model, I always like to pick on Hawaii on this. The weather forecasting model says your skill level is degrading for your forecast of Hawaiian weather, and so you need to collect some more data and improve the quality of that model. So the model knows that if you get sea surface temperature and surface winds over the Sea of Japan, you can fix it and everything's fine and the sun is shining brightly in Hawaii yet again. And the autonomy part of this takes that information and then decides which assets are available to go collect those measurements and then tasks the optimum collection strategy for the data that you're getting. So maybe you've got satellite overpasses in 10 minutes and you just have the satellites collect the data, or maybe you don't have anything for 3 or 4 more hours from space, but you've got a couple of ships and you've got you can launch an airplane out of Yokota, Japan and have it go make some measurements and provide the data that you're looking for. So, there's a lot of complex independent decision making involved in terms of all this tasking. So that's where we feel the autonomy becomes the most important aspect. I mean, that's the thing that drives the autonomy, is this automated system selecting the observing assets to go query and collect the data and bring it back and so on. There's a second aspect to this, and that's the research, science research for let's say hydrology or flood prediction. We're trying to improve our flood prediction models, and they need more data in order to do that. So they're monitoring river flow and stream gauges and stuff like that, and come to the conclusion that they need some satellite overpass data, maybe some GPM data or something like that, in order to understand why the models are starting to fail from the observing that they're getting from the stream gauges, and so it tasks a satellite to go collect the data and bring it back, and then it's used for improving the quality of the models and its ability to forecast future events. So there's really two aspects to the way you would use this kind of an observing strategy. I'm not going to go through all the details in here, but a lot of the work that needs to be done, there's really a couple of components to what needs to be done. The primary autonomy things that need to be developed involve the algorithms for the use of the autonomy and ways to, some of those have been developed for other applications, but they've never really been applied to this sort of model-driven observing strategy, and so work needs to be done in that area. There's a lot of work that needs to be done in supporting technologies, and I'll just cite that the safety and the testing and the computer security all benefit from from autonomy components, and those are areas, but they're not the primary function in order to achieve this capability. There's a number of programs that are going on, and I've tried to list some of them. There's a number of DoD and NOAA programs that are going on in this area as well. National Science Foundation is doing a lot of work in autonomy that we think can be applicable to this. The AIST program, of course, my program is working in this area, but there are a number of other satellites that we think we might be able to take advantage of. And we developed I'll talk about that in a minute. We developed a strategy for how we could take advantage of those assets and get smarter and smarter and smarter as we work through the process. Let's see, so why do we need autonomy in this? Fundamentally, humans can't respond fast enough to the changing conditions and to the complexity of the observing environment in this situation, and so we need autonomous operations in order to make this work smoothly without adding 500 people to the mission ops community and that kind of thing. So there is a cost associated with trying to accomplish this. This kind of approach is not currently in use in earth science, and so there's a lot of unknowns involved in trying to move to this model. We think that it'll improve the quality of forecasts, it'll improve the way we go about doing observations. It's very likely after it's been developed fully, it'll improve the cost of a lot of these missions and provide a lot more science data that we can use more effectively as a result. So we developed a number of other ideas that we wanted to bring out in this, and one of those is the implications of autonomous missions and earth science observing strategies. So we need to, some of these are policy, some of these are culture, but we need to start to understand better how to prioritize the observation of transient and transitional phenomena, these sort of short-lived things that currently we observe only by accident, but many of the science community people would like to observe with more deliberateness. Secondly, and probably the most important one in earth science in NASA today, is that we need to learn to accept more risk. We need to be in a position where we can fly missions that have a higher probability of screwing up, of not necessarily failing catastrophically, but not necessarily being optimum all the time. These things tend to get a lot of attention in NASA management, and that's usually never a good thing. I don't know of any PI that really wants to have management attention applied to their project, especially NASA management attention. We're currently flying, most of the satellites we fly today are really one observation, one instrument, they have one science team. They're really single use. We had an expression that I wrote down, but I don't have it on my slide. Anyway, single use type missions. We'd like to get to a point where we start to understand multidisciplinary science far better. And I think these are culture changes and policy changes that need to be adopted for this kind of strategy to go through. One of the things that we came up with was that at the senior reviews, when I can't speak for the other parts of the science mission directorate, but in earth science, after a mission has flown the requisite period of time and we've achieved the mission objective, same thing, okay. And we've achieved the mission objectives, then there's a senior review in which they almost invariably decide, unless the thing is falling out of the sky, that they're going to continue it and just collect more data. So, for example, Aqua and Terra have been around. They were 5-year missions, but they've been, what, 25 years now or something? Anyway, the end result is maybe those missions could be redirected to do some experiments with the technology in order to try new things, including multidisciplinary science. The A-Train is an example of how these instruments and satellites were originally put in orbit to do specific things, and then the A-Train was created by repositioning the satellites so that they could do multidisciplinary science. But in order to do that, there has to be some forethought to how you design those spacecraft so that they actually can be used for other purposes besides what they were originally designed for. And that's usually the stuff that gets cut when the budget starts to overrun. So thinking through how we would accomplish that guidance would be certainly useful. Provide some incentives for interorganizational collaboration. There's not a whole lot of that. There's a lot of interorganizational collaboration, but it's because PIs and other people have learned to trust each other from other things. And so they do it because it's a good idea, but they're not incentivized to do it from the competitive solicitations. And then there needs to be some adjustment to the command uplink policy that right now requires humans in the loop for if it's an instrument on the space station. It would be useful if we could do that without humans in the loop, and then autonomy would be more effective that way. This is a list of the autonomy mission, the sort of missions, the DRMs that we came up with that we thought needed autonomy. We picked just one of those, but it's in here for completion. And as you can see, there's one of them that's a phased array of satellites that would improve the quality of the data that's being collected and be re-steerable. And the autonomy part of this is the station keeping decisions that have to be made, or the re-aiming. I didn't get a chance to fill in that, but I'll do that later. And so we developed some ideas about near-term experiments that might help us with some of the key issues. So one of those was using OCO3 and to experiment with the targeting strategies, and I'm probably going to get this wrong, so any of the members of the group feel free to correct me. But we've collected a lot of data, and if in the future what we could do is go back and reanalyze that data with a autonomous tracking scheme, we could then say whether or not we collected the optimum amount of data, or how much better or how much worse we would have done that with autonomy. We can also potentially reuse the Tropic and Cygnus missions to test retargeting strategies using autonomy. And I'll add that we're discussing, AIST is discussing with the Asteria community whether or not there's an opportunity to take advantage of that and do some experiments that might get us smarter about how this stuff works. We can also provide a foundation for autonomy to be more extensively discussed in the next Earth Science Decadal Survey. So we generated a list of candidate DRM white papers. One of those is entitled Autonomy and Model-Driven Earth Observing Strategies, and that really describes the details of this particular kind of a mission. Smart train retargeting and the policy and cultural implications of the application of autonomy to Earth science observing strategies were two more that we thought might be useful. And that's it. So.
Great stuff. We have 2 minutes, which is perfect. Keep the mic. If there's some questions, that would be great. I've just got to switch over to another presentation. And there's a question at the back. Okay, don't start yet. And then when you're done.
So you're presupposing that I actually can answer any questions.
Okay, I'm going to need to be where you are just so I can switch over the presentation. Go ahead with the question.
So when you mentioned single mission, I was wondering about the idea of enabling, so basically having a tech demonstration mission as a tag along somehow, so that you have the main mission, but if there's a way to support funding to basically have some autonomous capability, as an add-on?
Yes. Okay. So almost, it's, okay, so now I'm just going to speak for myself and not the group. And they may agree with me or they may not, and they certainly are welcome to respond. But I think that we need to add some of those capabilities on so that after we've completed the original mission for a lot of these spacecraft, we could do more things with it that don't necessarily jeopardize the original mission, but then can, during this sort of experimental period, give us a lot more opportunity to try some experiments.
Great. Other questions?
Did I put everybody to sleep?
Not at all. Good
Sure I
stuff.
did.
No. Okay, so thank you very much. We have 2 left to do. And next up, I think we have the small bodies group. So whoever, I guess, I said you're the spokesperson. Okay, got it. Thank you so much.
Hi, so we had a very lively group of something like a dozen people, and talked around and around. We did not fill out the chart, but came up with what we thought were some interesting ideas. Hopefully you will as well. And there is the list of the participants. So we started by, whoops, where? What? There we go. Okay. Yeah, so what we started with was, what are the science drivers for small bodies? And one of the issues is that small bodies, unlike there is the moon and there is Mars, there are 600,000 or 700,000 numbered asteroids and a lot of Kuiper Belt objects and so on. So it's very broad. But Small Bodies Assessment Group, we've kind of gone after what are the basic things that a lot of small bodies issues have in common. And so those were the kinds of themes we tried to emphasize. So in terms of science origins, how the solar system formed, that sort of thing, and the big science questions related to that we can address with missions are things like, what is where, just finding out the architecture of the solar system, what is the composition of things, the precursors of life on Earth. We're not looking for life on an asteroid, but things like, where did the water come from? Where did the organic molecules come from? Things like the evolution of the solar system, the processes that have gone on to take things from where they were 4.5 billion years ago to where they are now, processes that are going on today. And so in those aspects, we're addressing things like compositions of things. Again, what got where? Geotechnical properties. What's the inside of a 10-kilometer asteroid like? Is it a rubble pile? Is it what? A part of small bodies is also planetary defense, because the moon's not going to run into us, but small bodies might. So the big drivers there are first assessing the threat, which is basically figuring out, again, what is where, figuring out the mass of the objects that might be potential impactors, figuring out their geotechnical properties, their interiors, that sort of thing, then figuring out how to mitigate them. And one of the big questions there is just, what's going to happen to this thing when we try to do something to it to move it? And finally, resource utilization, where we have to figure out an object could go to, have to figure out what is in it, whether it's something we're interested in, and how we might get to that thing of interest. So in terms of what is where, what size we're interested in depends on what you're interested in. What size we are interested in depends on who we are. There are people who are interested in things less than 10 meters. There are people who are most interested in the things that are tens of kilometers. We would consider things up to the size of Pluto and Ceres, but we did not for today, because we think a lot of the very interesting questions there are the kinds of things people like Ocean Worlds would be talking about. So we focused on the idea of smaller bodies where there is little enough gravity, just enough gravity to be a problem. So, 10 to the minus 6, 10 to the minus 3 G, something like that. And I want to emphasize that there is a diversity of small bodies. Every one you go to is likely different in some way, particularly when we've only been to a handful out of these millions of objects. What are we interested in composition? Volatiles. Water is a type example that stands out, but other compositional things as well. Water is important for everything from astrobiology to how did we get icy planets out there, rocky planets in here, to things like resources. The geotechnical properties. This is a place where we are profoundly ignorant of what a 10-kilometer object is like. What will happen when we touch it? Will it fall apart? Will we bounce off of it? We just don't know. So how would we do this? Well, in terms of figuring out what is where, what's going on right now is ground-based surveys, but telescope surveys in the next 5 to 10 years, we will have a space-based infrared survey coupled with one large ground-based survey. The issue here, though, is that we need to figure out how to follow up the discoveries that these things will make. We want to get to knowing 90% of the objects 140 meters or above that are near Earth objects. We know about 15% right now, so there's a data problem that Autonomy could help with there. Composition, the thing that would revolutionize what we're doing is to be able to go to a lot of different objects, even a flyby, but getting close would be even better. There are things about composition that need surface contact. If we want to know some of these diagnostic things about origins like isotopes, oxygen isotopes, that sort of thing, we need to get close to the surface. And geotechnical properties, a 50-meter asteroid or even a 10-kilometer asteroid, is it a rubble pile? Is it a rock? We can get some clues, but we really need to get at least into orbit and maybe send a signal through it, maybe try to get down and touch it. And if we get to the surface, then we can do things like seismic surveys, GPR from the surface, ground penetrating radar, and even just touching it tells us something. And so, is this where I turn it over to you?
I think so, yes.
Yeah, okay, so I'll turn it over to Issa.
Yes. Thank you, Tim. And thanks to the group, actually. It was a lot of great discussion this morning. Just to give you a sense, the first part of the morning session was mainly focused on understanding the drivers. And the second half in the afternoon, we focused on what is it that we can and cannot do with autonomy. And so a lot of it was on the engineering and the mission discussion. We looked at capabilities, which I'm going to go over. We didn't delve deeper into the technologies, but I think that once you know the capabilities, once you know the scenarios, you can figure that out. So what I wanted to talk about this picture here, and just to, for those of you not familiar, 67P, there's quite interesting things you would notice. First of all, extremely rugged topography, which makes anything to do with getting to the surface or interacting with the surface very challenging. You notice the white things around it, the venting, which actually came into the discussion regarding what it would mean if you're on the surface. So mainly what we focused on the afternoon, and we started, what is it that we cannot do without autonomy? Because there'll always be, if you can do it without autonomy, then that will be the solution that people will adopt. So it boiled down to this thing, which is interacting near or on or into the surface. And when I say near, I think it was Sham was saying it was actually very near, which we're talking about 50 meters. So once you get within 50 meters of the surface, or you get on the surface, or if you try to do something below the surface, it became obvious within the group, and I think there was a very strong consensus, that this problem does require autonomy. No question why. You are dealing with low gravity. You are dealing with a situation where there's dynamics. It's slow dynamics, but there's dynamics that does not allow you to wait to get a response. And there are changes in the environment. And you interact with it. You're changing the environment. You're changing your state in a dynamic fashion. Surface is extremely rough. And also there's another aspect, which is there's a dynamic phenomena happening on comets that actually can't perturb you on the surface. So where does that manifest itself? It manifests itself when you're into the final descent phase, trying to get to the surface. It also manifests itself when you're trying to understand surface properties, whether it's for science or engineering purposes. You're trying to collect the samples, or you're trying to grab and hold on to the body, and you don't know what this material is made out of. You can touch it. It may be friable. It may act in ways that you have not modeled before adequately. And if you're trying to do anything on the surface, you need to have some kind of a robotic mechanism. And to be able to achieve anything with the interaction with the surface, whether it's mobility, whether it's sampling, whether it's excavating, the dynamics of that environment does force you to have autonomy. So handling the environment, we talked about the dynamic conditions. Again, due to outgassing, actually, we were told in the group that there's sometimes meter-sized blocks of ice that come off these small bodies. So an example was Hartley. So it just gives you a sense of the environment you're in. Not only the surface is harsh, but there are things, there are activities, there are events on these things. And sometimes there's scientific interest to get close and sample. You are getting close to something that is dynamic, strong science interest to get into the stuff below the surface. And hence, again, you need to react, so you need to be aware of your environment, you need situational awareness, and you need autonomy. Access. We talked about access, and specifically we use the word access and not mobility, because we don't want to rule out any particular technology that allows you to go to different places. So access means I want surface access that gets to certain destinations within specific time frames, within specific uncertainty bounds. So we talked a lot about dense versus sparse. We talked about we want to be able to target certain areas for sampling. We talked about taking seismic measurements on the surface. And all these things will actually drive some level of precision maneuvering on the surface, whether you do that by having a spacecraft that lands and moves again and lands and so forth. That's one option to do that. Another option may be to deploy some surface platform that can do that for you. What was concluded from the team is that if you're trying to do anything within a precision of less than 25 meters, you can't do that from the ground, period. You do have to do that in situ. That's it. Okay. Another aspect is mobility, manipulation. By the way, if anybody from the group, please feel free to interject if there's something you'd like to add and so forth. So one other thing with manipulation is really understanding and resolving sample properties for collection. We talked about there's different grain sizes. You don't know ahead of time. You can't resolve some of these things when you're flying by the small body or when you're orbiting the small body. And some of these things will have to be made on the surface. One of the challenging things, you may be on a mission where you have limited resources, you may have limited time, and you have to make decisions in situ. Another thing that came out in particular when you're trying to get below the surface or trying to collect samples, which is, we call it anchoring or holding onto the surface. As you can think creatively of many ways you can stay put without putting enough force to take off. And so we didn't want to specify the particular technology, but anything related to that does require on understanding the instantaneous local conditions. And notice the word instantaneous, we had this discussion, is that you don't know how the surface is going to react. You may try to hold on to something, it may crumble underneath you, you may push some pressure on the surface, it may, it may react in ways you cannot predict. And so it is very important to be able to dynamically react to this, to these things. And you remember, even with places we've been to before, like I usually give the example of Phoenix and sampling, and you try to predict what these ranges of possibilities, and then space always throws you a curveball. In the case of Phoenix, the scoop was end up being more sticky than we ever imagined and stuck to the scoop. So there are things like that we can imagine with small bodies, especially given their diversity, that would make relying on a priori knowledge very risky. And again, back to the whole risk argument. Okay, sampling. Again, there are a number of places where you want to go after a particular sample or whether you want to go after sampling event. Be very interesting. Another thing is ISRU. We talked a little bit about that, and we looked at, there's this part of 5 minutes, okay. Our ISRU that you need to get below the surface. There was a discussion whether it's 0.5 meter, 1 meter, or 2 meters, but somewhere within that range to understand the resources. And then there's the whole challenge of extracting these resources, which is related to moving bulk material. Planetary defense requires an understanding of the composition, geotechnical properties, as well as mitigating these risks, if they are. Okay, so there's two key benefits. One of them is scalability. Basically, what autonomy for small bodies allow you to do is then, by having this autonomous spacecraft, you can scale that to having multiple such missions go to the large number of destinations of small bodies. Now, of course, we just discussed, well, why don't we do that with small satellites? There's a lot of interest in small sat, a lot of technology. That seems to be a nice marriage between the two. So Carolyn raised a concern about, well, these are not exactly where you want them to be cost-wise. Another person raised a concern about communication challenges. But the idea is that we're looking 12 years out, and hopefully with advances in small satellites, costs will come down, these things become accessible, and we're able to scale to access multiple bodies. And then the other thing is agility. By having autonomy for small bodies, and given that there are a large number of them and we're constantly discovering them, that how can we react? How can we rapidly get to different asteroids and small bodies, comets, and interstellar visitors? So I'm going to indulge you with this futuristic scenario. So think 2040 plus, and then we'll come back to reality in the next scenario. So in this scenario, what we envisioned is some kind of a centralized mother platform that's launched, and you launch and forget that, with a bunch of daughter crafts that are small satellites. And what this mission does is actually you have now multiple daughter satellites exploring the diversity of small bodies. Then you identify targets of interest. You go reach these targets of interest, whether it's an opportunistic interstellar object, whether it's a hazardous object. You get there, you collect your samples, you bring these samples back to what we call the centralized platform, which is a gateway-like. You analyze, you extract resources, or if you need to divert them, you can divert them. So that's kind of the very futuristic scenarios, multiple spacecraft, the whole mission is done autonomously. If you take that scenario and look what capabilities you need, what autonomy capability, you need management and coordination of multiple assets. Can do that either from the ground or in space to survey, monitor, and characterize and identify targets. Then the other aspect of it, the whole mission to go from that to the target of interest, that whole mission design could be done autonomously. Autonomous characterization, approaching and landing on the surface, then precise targeting areas on the surface, then operating on the surface, whether you're doing mobility or you're taking measurements. While you do all these things, when you do everything autonomously, you have to understand the spacecraft, its health, its resources, manage that, and do all these decisions autonomously. You conduct your science autonomously, including the decision making. If you're doing excavation or you're trying to divert or do any kind of extraction, you could be manipulating large blocks. You can be refueling in situ from the resources, or you can return to the platform and do refueling at the centralized platform. Very ambitious, very long term, but it does address a couple of things, which is the diversity of the targets you can go to, and as well as the opportunities that may come up with small bodies because we're constantly discovering them. So now we turn it to something, how can we take this very ambitious vision, turn it into something more realistic for the 2030s that NASA could possibly consider. All these things that I just talked about could be achieved, or a smaller scale version could be achieved with one small satellite. So imagine you have a small satellite, you fire it, and you put it in Leo. And then you do have a high-level goal of having that find an asteroid. Then you autonomously cruise, approach, land on that body, precisely accessing at least one target on the surface. Now we're doing mission requirements and trying to be very conservative here. Sampling, analyzing, and send the publication back. All that done autonomously. Okay? So there's a bunch of technologies from the previous one we don't need, but there's a couple of overlapping things, which is the identification of an asteroid based on some intent you provide, doing the mission design, doing the cruise approach landing, characterization, precision targeting, autonomous operation, health management, and in situ science. I know I'm up. Just give me 1 minute to cover 2 more slides, if I may. So that's basically where we ended up. There was 2 more things I wanted to share with. We had a number of conversations, which is a lunchtime conversation about, which is in the spirit of this workshop, how do we engage industry? So from that conversation, 3 things came out. One of them is industry would like to see crisp engineering challenges that are presented to them to be able to attract partnerships so they can work on these. There was another thing that came from the conversation is to scour a bunch of DoD activities that have government rights and offer them to the proposing community, science community. And then assess applicability of automotive computing, sensing, and reliability standards and capabilities, because autonomous transportation is going to look at human-rated type of capabilities, their standards, and what of these things will apply, where if there's some alignment at some point in the future, perhaps it will make interoperability of some of these components easier between NASA and this large community of autonomous vehicles. Now, there is something I would like to close with one thing, that autonomy for small bodies actually has value beyond small bodies. It basically provides you a playground for developing autonomy, testing it, maturing it through a series of more complex missions. Why is that? So first of all, for small bodies, there are three things that would be valuable, which is science, planetary defense, and ISRU. And there would be industry interest in the latter, general human interest in the middle one, and scientific interest in the former. And the other thing is they're accessible, they're plentiful, and they're diverse. And we've only observed 15% of what we project the number of small bodies to be. But key thing is they embody challenges that are cross-cutting across several DRMs. And one of them is you have a body that's accessible, that has very interesting topography, and that has mapping challenges. The surface is extremely rugged, similar to surfaces that you may encounter on Europa and Enceladus. The interaction on that platform is dynamic because of the things I talked about. There's dynamic interaction will be with Venus balloons and Titan balloons. If you get into a liquid body, it's a dynamic interaction. They're a more affordable place because the lower cost for doing approach and landing. So EDL is usually extremely expensive thing. And with small bodies, it's an easier problem, but it has all the elements of being able to perceive the terrain, sense it, make decisions, and land. And because the dynamics are slow, you're afforded a little bit more time. Not to mention the other places are more difficult, but if you can do that fully autonomously here and you have reusable elements, you can afford, or you learn a lot to do that elsewhere. It's a little bit more forgiving because of the low gravity. The impact with the surface is less. Almost done. And then it's accessible by smaller satellites. You don't need to have large solid motor rockets to decelerate and take delta V out. And you have all the properties. This is an unknown surface. You can get below the surface, and you can get around the surface. And also, it offers missions of opportunity. You get an interstellar visitor. If you have an autonomous capability, you can react to that quickly. The planning and everything you need to do to get that mission could be a rapid turnaround. So I would close by autonomous capability could pay for small bodies, could pave the way to being able to do autonomy on more remote, more expensive, more far destination. And I think it could provide a stepping stone, a playground, not to mention all the science value that Tim talked about. So thank you. Sorry to take long.
That was very good. Well done. I thought it was particularly great that you mentioned specifically the partnership with commercial commercial partners. I thought that was great because I know that was a really important part of our conference. Okay, you're doing it from here and going straight to the video. Okay, we're going to do a quick laptop change because we've got intriguingly a video to follow the presentation. And this is the last presentation right here. After that, we've got some closing remarks, just a few more comments on practicalities, and then you get to do all kinds of fun stuff with AUVs. So, let's hear this last presentation and give it all our attention. I think it looks really interesting. Go ahead.
Thank you, Graham, for letting us slide in here with changing the computer. Changing the computer. This is the Ocean Worlds breakout group. If you remember from yesterday, it's been a long couple days, but very exciting. There were three sort of missions that we were thinking about, concepts. One a fixed lander, one a mobile system on a Ocean Worlds, and then one a deep cryobot type through the ice concept. Bringing that down, we said if we're looking 10 years out, what should we be thinking about in terms of the autonomy mission? And we brought that down to the cryobot and the what we're called the crevasse explorer. The team shown here, about 10 people. What was great about this team was that we had a mixture. We had science in here, We had remote sensing instruments. We had in situ instrument science. We had pure autonomy, if you want to call it that way. We had technology drivers, and we had mission set. We had software end of it. We had hardware end of it. So it was a really great combination of folks, and I think it was some of the best discussion I've seen in a breakout session, something like this. Bill McKinnon started out, and he described the ocean worlds. There's maybe upwards of 2 handfuls of them, defined by having a large body of water, maybe frozen or liquid. As he described at 9:30 and midnight, the poster children today that have a large body of water that is sitting on top of a rocky core with an icy crust just has all that interest to it scientifically. And so Titan, of great interest that's moving forward. For looking at autonomy needs, we focused on those 2 bodies to move forward. So being human not in the loop, no need for humans, and being an autonomy, we sent our mission design, our autonomy design bot off to go build and describe the ocean worlds, in this case the CryoBot system. So what you're going to see here is looking specifically at Europa and what is feasible. Actually, Ruja, can you hit the lights over there if you can see it? You're seeing the water maybe about 100 kilometers on top of the rock, and perhaps this 10 to 30 kilometer ice sheet. This is obviously this is a video that JPL had in-house. Bill was telling me just keep lying, just keep lying. There is a but what you can see today is so wonderful. You're seeing a smell test on a landed system. You could borrow from oil prospecting that puts down a cap onto the surface. Obviously, you're going from vacuum into ice, so you're going to sublimate in the beginning. You're not melting, and so you're trying to build up pressure inside the cap. To this entry in a system like this is essential, and so you'll see a cutting system that's going to move through, as well as water jetting and heating in a probe like this. So now we've entered into the ice, that we're in the crust, and because of the extreme radiation, at least at Europa, the idea is that you leave the electronics package about 1 or 2 meters beneath the surface to protect it from the radiation. You have a tether up then just to an antenna on the surface. Communication through the ice would consist of transceiver pucks, both acoustic and RF, that would perhaps every 1, 2, 3 kilometers be able to ping data back up from your CryoBot back up to the surface, using both RF and acoustic, depending on how much water is in the how much water in the ice as it warms up. Huge autonomy system right there. You're looking forward in the ice, maybe with radar and sonar. Perhaps we could go 100 to 200 meters ahead of the CryoBot and look if there's a void, if there's a sediment layer, if there's some other obstruction, and then you could steer around it by perhaps differential heating, differential water jetting. Some 10 degrees have been shown in Earth systems. Now you've hit the ice water interface. You found a way, and you slowed down and you went through it. And at least in this concept, you bring forward and drop into it the forward section of the CryoBot, and you're going to open the door. And here we prototyped what was a buoy, an underwater vehicle. In this case, it's a buoyant underwater vehicle that, making it buoyant, it will float up to the top, to the roof of the ice water interface, and then with wheels you could drive on the roof. The scientists again tell us that life exists at the boundaries. That's where the energy layer is. It grabs the energy. We see that on Earth. This vehicle, actually a little larger variant of it, has been put through holes on Earth in lakes and up in the Arctic and in California, and driven around like this here. Obviously you turn on the light, and you go forward and you look for, this is the part where you're starting to, you want to get out there and look for hopefully extant life or potentially extant life in that water. On Earth, when this vehicle goes underneath ice sheets, you do see bacteria, you see some kind of mats on top of the bottom of the ice sheet, ice layer above the water. And then when all goes well, of course, you're pinging back the information up to the surface and then back to Earth. And we're all going to be very excited at that point.
That's what we call a breakout session.
So at this point, we're done. Thank you very much.
Okay, so
because of our autonomy
we
bots.
definitely have time for questions.
No, I'm just joking.
Moving on. No, you're good. Keep going with your presentation.
At this point, we said, no, Florence is not going to be happy. And so we went to the, we had a lot of discussion here, and the discussion all revolved about that's sort of the concept, just to set the scene, so we don't have to go into any more of the details. But this was all about prioritization, and we said, let's walk through the taxonomy. Let's start at the high level up front, have a discussion on what are the highest level needs for autonomy for something like this. This is the CryoBot. We have a second page for the Crevasse Explorer. And then let's walk through them, and let's prioritize the autonomy needs. There's hardware that's needed, et cetera. And let's break those away and only think about what we need for the autonomous system, so to speak. And so the top there is the discussion on the detect life in the unknown environment, the CryoBot mission. And right off the bat, we broke it into engineering autonomy and science autonomy. And even though it's sort of an artificial construct, because you don't want to go that route, it really helped us at least form the discussion, I thought. And what became important is the science autonomy was kind of driven. There was a lot of discussion yesterday, is that you're not going to build you're not going to cram, for example, you're not going to cram a rover into that vehicle and then send it down and then operate it with sequences later. And so the science autonomy was a real driver, and we had a lot of discussion about it. And then that feeds back on the engineering autonomy, and they have to blend together at the end of the day. So the science autonomy, I'm going to walk out here so I could read my writing. The science autonomy was all driven by you enter into the ice crust, and you're in a region that you've never been before. You have basically very little information about it. So there's a lot of discussion about model-based autonomy, is that we have a model. For example, the minimum model we have says it's about 100 Kelvin on the top, it's 273 at the bottom because it's liquid water, and there's some gradient of the ice, of the temperature in the ice. And that drives a lot of your CryoBot performance. But when you go in, you're going to start learning about this ice sheet. You're going to learn about it through a body of sensors. What sensors would you like to have? That's the sort of discussion we had, so that we could form then an autonomous science system, which feeds back to the autonomous engineering system, which feeds back to the autonomous science system, and it blends together in the perfect world if we move forward. So the science autonomy was to perform real-time adaptive science with limited a priori knowledge. And this means that you can't do this mission without some level of autonomy sitting there, thinking for itself, deciding what to do for itself, because you can't send it back home and get a person in the loop. We broke up the engineering autonomy into the descent through the ice. It was fundamentally different than the autonomy for under the ice roving. These are the highest level concepts that we believe we could drive then a lot of the tech development and get to some conclusions at the end. Then when you look into then we went into the taxonomy, and if you go back to that essay one, the science autonomy, the key one, it was all about this learning and adapting, the 2.7 in there. If we need to do something over a 5 to 10 year period, it's to bring a set of instruments into something like this environment where we have very little knowledge, and be able to start moving through that. And this is about maybe it's a 2 to 3 year time frame to get from the top to the bottom of the ice crust. and start moving through that ice crust, learning along the way. So this is sort of like turning on your self-driving car with very minimal information about the environment, and learning as you drive along the way. And at the end, you're going to have all the knowledge you will ever have. You're not going to train ahead of time to a large degree. And so that we believe is actually the number one research area that should be started up, is this something that will create the real-time adaptive science with limited in a system with limited a priori knowledge, limited data, limited power, limited resources. And then as you go forward, obviously fault diagnosis and the prognosis for that, fault response, these areas that drive it, we sort of kept going back through the taxonomy and say, what are the highest ones, what are the highest ones? And that list up there fell away. Hazard assessment, meaning hazard assessment for science, there's something interesting there. It's not really a hazard, but there's a large gradient in the salinity. There's a large gradient in the temperature. It means something to the scientifically, and so we want to move forward and go examine that. The probe is always moving. When you turn on the radioisotope source, you can't turn it off. It's always going to be moving. You could slow it down, maybe you could speed it up, and so you have to be doing this in real time as you go forward. So as we looked into, we said what's going on outside of NASA and what's going on inside of NASA. The decision-making algorithms, we believe there's a lot in industry. The sensor data integration, we believe there's a lot of industry. How you put this together for the science, obviously, is a NASA question. But we believe you got to find a way to get at that work in industry, like we learned about yesterday and a little bit today, to bring that forward. Jumping just to the end, this is enabling this mission, this concept, this autonomy is put together in such that it's a one-way light time. Prohibits human in a loop. You just can't do it. If you're only looking 100 meters ahead before you make a decision, even if it's 100, how much time you have to bring it back and forth, you're going to be limited. You at least have to do it autonomously. Again, the things we mentioned there. And then we said, what is the longest thing? That's 2.6 and 4.1. 2.7 is the science autonomy. We have to start that today. We have to get going on that today, because that's a 5 to 10 year thing. We don't know how to get started on that. We did just 1 minute, very quickly, less than that. We then said the Crevasse Explorer, and what we did was a delta. We said, okay, if we did all that, and we learned all about the Deep Explorer, which is the hardest mission, what's different if we just landed on the surface and we needed to have some set of mobility, hundreds of meters, to get to the edge of the crevasse, because there's a plume, for example, plume material there, and then go into the crevasse. So it's a separate mission. We just want to look at the crevasse area. And basically everything was the same, except for we have this mobility part, and so you had path planning. You had this planning part that says, now that you landed, how do you get to that point you want to get to on the surface in this really chaotic, European Enceladus environment. So with that, we'll leave it, Graham.
That's fantastic, Tom. Thank you. Good job. Okay, I'm just going to switch back over to, this is your dongle though, Tom. You won't want to forget that. While I'm switching back, I always wondered what the math would be in terms of the power requirements to just drop a spherical probe that could melt its way all the way down, and then drop some ballast so it became buoyant and melt its way right the way to the top again so that it could transmit. But I think too much power, but it sure would be a lot easier. Okay, so let me get this back up and running. Got to find the right, not that one. Hold on, got to find the right slides because we switched over. Presentation, day 2. Here we go. Okay, well, hats off to all of you for managing to get us keep us pretty much on time. That was very close, because that's a lot of material, and I'm sorry that we we're able to fit in a little more Q&A because I know that that's important. Here's the good news: is all that content already put into a shared Dropbox. Florence, you have access to it. Lisa as well, and all the DRM leads. So that's what you wanted to get out of this. Is awesome ideas. There were already a big list of white papers, and many more to come out of that. Now imagine that those move forward and what we could do with that. So. Listen, let's move on to some closing remarks by Mike. I know he's been thinking about this. Then we're going to give you a couple of points on the evening, what's about to take place, and also some thoughts for tomorrow. And we will close the event at that point. And I'm looking forward to seeing what comes of the UAV demo. Go ahead, Mike, and I'll fill you guys in on the details in 1 second.
Okay, so the demo's at 5:30. How long does it take for us
Is that on? I don't think that's on. There you go.
You should allocate 10 minutes to get 50 autonomous agents.
Okay. That is definitely what we are.
So 10 minutes to walk from here to there, and okay, so the arrival time is 5:30, not the departure time. Okay, thanks. So thank you, everybody. Really appreciate it. It's a lot of information to digest. We'll be working. We want to keep the teams together over the next 6 months or so. In the Earth breakout session, we talked about having, is it monthly meetings, or are we doing bi-weekly meetings?
We're having bi-weekly face-to-face meetings in Tahiti.
There you go. At my expense. Okay. You know, we're live streaming, and okay. Anyway, all right. So so I would encourage. I'm assuming the other teams will also keep in contact. In particular, we're going to be compiling the notes. We'll be putting together the white papers. We'll be iterating with your groups on those white papers. And then, as I mentioned this morning, the plan is to have a session at AGU, along with a breakout at the assessment group meetings or NASA headquarters. So just, kind of doing an overview of what we just heard, there were different levels of technology gaps that I was able to discern, but let's push back if you think that's not the case. There was a class of autonomy, I would call it in situ optimization of observations, given a set of sensors, satellite collection assets, remote sensing assets. There exists an optimal set of observations to maximize a science return. And that's certainly true for Earth, for the Earth science case. And Mike, you articulated that in your DRM. That's also applicable for Venus, for the aerial case. Did I get that right? Cooperative, where a model or a collection of observations or just observations work in concert to maximize the science return. The model can direct the observations and maximizes the return. That doesn't seem to involve a lot of new technology. To me, that seems to involve taking what we already have and piecing it together. So I don't see a lot of low TRL investments in this particular category. What I do see the need would be to do some in-space demonstrations, which we never did 10 years ago with the Earth Science Sensor Web. And now we have small satellites, and we can perhaps do that. And maybe we could test Venus technologies as well. I don't know. Okay. So that might involve a higher TRL investment in technology demonstration missions. So the coupling together of all those components is where the the issue is, operating as a complete system, which would be not mature. The second category that I was able to pick out was kind of an in situ, handling, manipulation, sampling, and access, heavy on planetary science. The robotics will deliver different levels of capability, largely driven by industry, I would think. But then the specifics of how to manipulate, where to go, there's an intelligence behind that the algorithms would be uniquely NASA. Are you in agreement with that assessment? So the algorithms seem to be the secret sauce in that regard. What we just saw in Tom's presentation, he had learning and adapting. So you're going into uncharted territory, you're learning as you go along. In the video, you showed the submarine or crawling along the surface of the roof, you called it. What if that's slush, or what if it's not? What if it's? In fact, on the surface of Europa, I don't know if you saw the news articles the past couple of days, but they're now thinking there may be spikes 10 meters high. That maybe just to make it even more. You need to add that to the video, right?
I love that. I think we need to be careful about that particular.
Okay, good. Maybe it's not true. All right. It could be true. So there's a learning and adapting, and that could be tested in Antarctica, for example, or it could be, you could test that. Earth is an ocean world too, and you could test it in this environment, I assume.
Yeah, I didn't highlight it. One of the bullets on the bottom is that Earth science is very good at having airborne and field campaigns before you have operational missions and after you're in the lab bench. And I think there's many of these technologies we're seeing.
Thanks, Florence.
There are many of these technologies we're seeing today that need these field campaigns, even though they're not just pure earth science. They can be used for earth science, like all the ice going beneath the ice. It can be used.
Right.
Yeah, in the same vein that you can do orbiting and aero and surface work cooperatively. So I think you're on the right track, Mike.
Okay. Combining resources, so existing assets working together. Jason had mentioned that, particularly for Earth. What we didn't hear about was learning and adapting for other areas outside of the ocean world. So Isa, I thought yours was very complete in terms of end-to-end requirements, but I didn't see, even in your case, there wasn't a learning aspect to your example.
That doesn't mean it's excluded. It's actually, there is a significant component. One of the things that you look at, there's a lot of technologies. I mean, when we break it down to the taxonomy, you'll see a lot of these covered for small bodies. And clearly, because the terrain is unknown, the geotech properties are known, your interaction, you have to learn and adapt to be able to get to your destination. You can do a near-term mission where you just go to one destination, but if you're trying to hit multiple destinations, that's clearly the case.
Okay. And then finally, there wasn't a lot of discussion about failure recovery. And maybe that was because the emphasis that we had been placing was on science, but fault detection and recovery was not, I don't know if you had a chance to talk about that, but if people have any thoughts now, perhaps we could, the maturity of that, where we are with state of the art.
Yeah, that and the safety presentation that was this morning. We talked about that and how to address that. I think it's part of everybody's. It must be part of everybody's.
It wasn't explicitly called out what I just saw. I'm just saying it, yeah.
And we talked about it. In fact, Mars went over the entire DRM, and we actually went one by one and said, where is it? Because that's one thing that I had asked for in the DRM.
We talked about it in the Ocean Worlds group also, and the question was, do we just want a complex state matrix fault tree, or do we want some kind of autonomous intelligence behind it? And I think the latter definitely would need research, but I think we determined, at least for our very specific case, that there was only a finite number of things that we could do to take any kind of actions. And so that's why we said we'll just stay with the state matrix.
Okay.
For the small bodies, we talked about this as well, and we cover it under what we call system health management.
Yeah, so I'll share that this is a field that has been lying fallow at NASA. There's decades of research in model-based reasoning in diagnosis that we've been trying to infiltrate into missions, and we just haven't been very successful. But we have been doing recently some very focused research efforts that I'm hoping to get on Asteria next year, just like Jim mentioned. Using it as a test platform, but there's a lot of opportunity there. That's my message. We have a ton of research that's been done in the area, but not much has been infused yet.
Okay, great.
There were also discussions for Team Moon about the role in fault diagnosis and recovery, particularly in lost comm/no comm areas, where the onboard fault diagnosis and you're basically stuck with what you have if you want to keep the mission going. So even in missions that are close proximity to Earth, that's not a guarantee that you'll be able to recover or just always phone home.
Okay. I want to get Carolyn to talk about
internal and external. Internal to the vehicle, but also external to the surroundings.
So I think we're just about out of time, but I wanted to give Carolyn just, since planetary is a tall pole here, I was wondering if you had any closing remarks. I don't mean to put you on the spot, but did you have any?
Let's get you a mic.
Sorry.
Get this one.
Yeah, so the most interesting thing, I'm trying to manage the technology development for planetary science that isn't already in missions. And it was not obvious to me that there was going to be the existence proof of necessary autonomy for all of these missions. Your Ocean Worlds, I get it. We spent a lot of our time in small bodies really debating that point. And so one of the interesting things to me is that, I think everybody made a convincing case that autonomy is actually needed for the missions that you came up with. And that's very interesting. I think that'll be a rich vein for us to mine.
Okay.
Yep.
Thanks, I appreciate it. All right, any other comments, remarks? Thank you very much. And we're not finished. We'll be continuing these discussions over the phone and over the next few months, so I really appreciate it.
I want to give Florence a chance to have her comments as well. And I'm just going to say this. You guys have all been to workshops, I know, where at the end everyone's brain is just fried. You're like, oh my God, get me out of here. This is a testament to how much energy you put into this. There's so much to discuss. We just can't get you guys to stop. So it's fantastic. I think it's a good indication of a job well done and a mission that Florence and I think you set us on this course. The tight collaboration with Mike being just absolutely key. Mike, thank you so much as well, because I think your contribution to how this all came together, I think, has been understated. So well done. Fantastic.
Thank you very much, everyone. And again, thank you for coming. Thank you for doing all this great work. I would like to also thank Brian back there, our videographer, who'd been doing all that work quietly. and our host, David, who's drawing you a map. Huh? And Bill Diamond, SETI. Lockheed Martin, the guys back there. Our Honeybee Robotics, I don't know. Yep, here we go. And one more, Zach was somewhere here. Yep. And Graham? I think we have Lisa over there, Lena.
Yeah, thank you.
Right. Mike Little again. And finally, of course, Mike Siebel, who made it all possible. Thank you. And Tom Zwick. Tom Zwick, I forgot Tom, sorry. He was our steering committee too. And guys, thank you all. I know I probably forgot to thank all the rest of the students and all the DRM leads, but really appreciate it. If you have to send me notes, please send it to me, email it to me, and if you have changes to the slides, please also feel free to add to it. Thank you very much, and enjoy the drone demonstration.
Yeah.